All right, 8.6 video notes. We're kind of getting towards the end of the chapter. I'm not going to learn any new trig today. We're just going to apply trig, solving angles and solving sides to some word problems. A little bit of new vocabulary, angle of elevation and depression, which aren't terribly important unless there's no diagram given and it's just words, and then you kind of have to know what those words mean to set up your picture. But the trig behind it is going to be the same as what we've done the last couple days, so hopefully it won't be too rough of a lesson. All right, so let's go ahead and we're going to start off with a definition here. I've typed it in already. I don't think it was on your note sheet, but you can write it in with me. Angle of elevation is the angle formed by a horizontal line and a line of sight, and this is the key word, above the horizontal line. All right, above the horizontal line. So as you're writing that down, I'm going to kind of set up the picture. So let's say that we have the ground down here, and let's say we have some sort of maybe a soccer ball or something like that down here on the ground, and we're going to kick the soccer ball. All right, so you're going to kick this ball up in the air at a certain angle, and this angle that it makes with the ground to up above, this is what we're referring to as the angle of elevation. Now, oftentimes there's a person, maybe, so another scenario is there's a person down here on the ground and he's looking up or she's looking up at something way up here in the air. All right, maybe there's a bird or a plane or something up there. Not a very good artist, so you have to bear with me. But the angle between the eyesight looking up at an object, that's referred to as angle of elevation. So from this actual point of view, this would be our horizontal line. There's the line of sight going up, and the angle of elevation would be this angle right here. I don't know why that's still being a dotted line, but so our theta here would be the angle of elevation. So basically it's going up from some sort of horizontal position, whether you're kicking something, hitting a golf ball, looking up at something, that's elevation. Now, angle of depression, okay, depression is very similar. It's the angle formed by a horizontal line and a line of sight below the horizontal line. So typically you have somebody standing on something. You know, maybe you have some sort of a big building and you have a person up here looking down on something, and I think one of the problems we do later on is they spot a fire. So they look down here to the ground, and there's some sort of fire going on down here. Tried to make it red so it looked like fire. There's some fire. So you got some fire on the ground. So the angle of depression is the angle formed by a horizontal line. So I need to draw in this horizontal line. So from my eyes, this would be a horizontal line. All right, and then my line of sight down. So basically the angle of depression is right here, and this one seems to be the one that people struggle with a little bit more. For some reason people want to make this one, now I'm going to put this in purple, but I'm going to cross it out here in a second. For some reason people want to call that the angle of depression, and that is wrong. Do not do that. The angle of depression, because there's no horizontal line that it's trapped between. All right, it has to be from a horizontal line coming down. Now, something that I want you to realize and understand that's going to help out in some other triangles is that when you are looking down on something, so say here's my person, and I'm actually looking down on something down here. So we say that the angle of depression is right here in this spot. Well, oftentimes when we solve problems, the actual triangle that we're working in is over here. And because of parallel lines, you'll notice this angle of depression has to match this angle down here because they are alternate interior angles. Remember back in chapter 3, if you have a set of parallel lines and a transversal cutting through, that this angle right up here, the angle of depression, is actually going to be this angle down here. So we're going to use that fact, the alternate interior angles, later on when we solve some of these problems. So alternate interior angles. And we know that they're always congruent if the lines are parallel. Alright, so a little bit of terminology. Let's jump in and try to start actually doing some trig. Now the hardest part for some of these problems is actually just setting up the picture. If you can get the picture set up, that's usually half the battle. And on short answer type questions, I'll usually give you some points for actually just getting the problem set up. So let's draw this one. A kite with a string of 150 feet long makes an angle of 45 degrees with the ground. Alright, I'm going to just stop right there. I'm going to go ahead and I'm going to draw this. So I have the ground. Alright, then we have some kite up here. Put this kite up here in the air. A rhombus. So there's my kite. And it has a 150 foot long string. So the string's going, it's really windy out. String's coming right down here to the ground. And it says it makes a 45 degree angle with the ground. Alright, so this is actually an angle of elevation because we're going up from the ground. So 45 degree angle. The kite string itself is 150 feet long. Assuming the string is straight, which it is, how high is the kite? So what we're actually after here is we need to know height, remember, is straight down at 90 degrees from the ground. That's the true height. So this is my H. Now, before I get too into this picture, I want to draw over here to the side some things that happen. So let's say you have some sort of object up here. I don't know, maybe it's a bird, and you have the ground down here. All right, and maybe you have some other object down here, like some little mouse, a little curly tail. It's a pretty crappy little mouse, but pretend it's a mouse. So this bird, there's a few different distances you may see in some problems. All right, so this right here, this would be the distance from the bird to the mouse. Okay. Now there's two other components to this. There's two other distances. This down here on the bottom would refer to the horizontal distance, and over here on the side would be the vertical distance. All right, so horizontal distance would actually be this leg of the triangle, and the vertical distance would be this leg of the triangle. And the true distance from the bird to the mouse would be the hypotenuse. So I just want to get those in your head about horizontal or side-to-side distance and vertical distance. All right, so let's get back to this kite problem. I think we should be able to set this up using some pretty basic trig here. So first thing is, my point of reference is always on the angle that's given. So I put my guy, or I put my point of view coming from here, and labeling the sides across from the 90. Okay, across from the 90, that's always the hypotenuse, and across from the 45, this is my opposite. So opposite and hypotenuse, I think I'm going to use sine. So the sine, when standing at 45 degrees, is the opposite leg over the hypotenuse. And I just solved this problem. So a couple different ways I could solve it. I could solve it by putting a 1 under the sine of 45 and cross multiplying. Or if I want to, I'm going to show you a little bit faster way now. Instead of doing h divided by 150, I'm going to just multiply both sides by 150. And divide by 150 times by 150 will cancel, and I should just get my answer here. I'll get h equals, and now I need to punch into my calculator 150 times the sine of 45. So 150 times the sine of 45, and I'm getting about 106.066. So we'll just call that, doesn't tell me what it wants, so I'm just going to call that 106.1 feet. And that makes sense. It should be shorter than the hypotenuse. So I think 106.1 makes sense in this situation. All right, let's go on to the next question here. Number 2, a tree that's 10 meters high casts a 17.3 meter shadow. So let's get this thing drawn. I have the ground. I have a tree over here. Nice green tree. All right. Casts a shadow 17.3 meters long. So kind of be careful here, because if you have the sun, let's say the sun's up here and it shines down and it hits it, the actual shadow is down here on the ground. So this part right here, this is the shadow. The red line there would not be the shadow. The shadow you see on the ground, you don't see it up in the air. And over here would be my height of the tree. So the tree is 10 meters tall, so this is 10 meters. The shadow down here at the bottom is 17.3 meters. And we need to find out the angle of elevation. So let's just go ahead and let's call this angle of elevation, we're going to call theta. We could call it x if we wanted to. Maybe we'll just call it x. So this is going to be x degrees. So that's what we're trying to find there, angle of elevation. So looking at this problem, my point of view, my reference point is going to be right over here. So here's where my point of view is. And it looks like 10 is going to be the opposite, and 17.3 is going to be the adjacent. So I got to find the trig ratio that's opposite and adjacent, and that's tangent. So the tangent at x degrees is the opposite over the adjacent. And now, whenever you want to find an angle or you're solving for angles, I know I need to use the inverse. So to get x all by itself, I need to take the inverse of both sides. Take the inverse of both sides. What that does is it basically makes these guys cancel out. And I get x equals, and I need to plug this in my calculator. Punch that in. See what shakes out using second tan if you're using the TI-30 here. So second tan 10 divided by 17.3 equals, and I'm getting about 30.02. So we're just going to call that 30 degrees. So that's the angle of elevation of the sun. It'd be about 30 degrees for this problem. You use tangent a lot, it seems like, in real life problems. So when in doubt, really strongly consider tangent in a lot of these elevation and depression problems. All right, next one. A plane is flying at an altitude of 12,000 meters. All right, let's get that out here. So here's the ground. Here is a plane. All right, pretty crappy version of a plane, but there's a plane. 12,000 meters is the altitude. So remember, altitude is just another name for the height. So the height of this plane from the ground straight down is 12,000 meters. From the pilot, the angle of depression is 32 degrees. So here's one I got to really be careful on. So the pilot's eyesight up here, okay, right? We're just going to pretend he's right at the height of the plane. His eyesight, all right, coming down, he's looking at an angle of depression of 32 degrees. So remember, first off, angle of depression is going down from horizontal. Okay, going down from horizontal. So the first thing I got to do is I got to look at where horizontal is. So here is horizontal. I'm going to go ahead and I'm going to just label that. That's the horizontal. And now the angle of depression coming down is coming down right here. And when I label this spot, this angle of depression, that is the angle of depression right there. Clean that up with a solid line. Angle of depression is 32 degrees. So right now, the angle of depression is not even inside the triangle formed with the ground. Okay, and I need to find out how far is the tower from the point directly beneath the plane. So we got to put an airport tower over here on the ground. Guess I didn't really do that part. Alright, this is where the tower is, way over here. 32 degrees, so how far is the tower from the point directly beneath the plane? So here is the point directly beneath the plane, and here is the tower. So what they're wanting to find, this is our x. We're trying to find how far it is. Now if they said how far is it from the plane to the tower, that would have been the hypotenuse. But they said how far from a point directly below the plane, all right, to the tower. So now I'm in a little bit of a pickle. I don't have enough degrees inside the triangle, but remember what I showed you before. Since this is 32 degrees, I can also jump down here and say that this is 32 degrees because of alternate interior angles. Now, some of you may notice and say, well, wait a minute, I could calculate this spot right up here and use that. You could if you wanted to. You could subtract from 90 and call that 58 and have your guy stand up there. But I'm going to go ahead and I'm going to put my person down here at 32 degrees. I like transferring the 32 down because I don't make a mistake. Sometimes when you subtract and you calculate this angle, you might make a math mistake and now the problem is going to be wrong because of a simple subtraction calculation. Alright, so standing here, I label my triangle. This side would be the opposite according to my guy. This side would be the adjacent. So again, this looks like a problem for tangent. So the tangent of my guy standing at 32 degrees is opposite over adjacent. So now if you want, you could put a 1 under there. You could put a 1 under the tangent of 32 and you could cross multiply. Or I think I've showed you guys before that you could just use a shortcut and these two basically just end up trading places. And I basically get x equals 12,000 divided by the tangent of 32 degrees. And I'm going to calculate that using the calculator here. 12,000 divided by tan 32 equals, and I get 19204. And this was meters, I believe. So there should be the correct answer, 19,204 meters, which makes sense because if I calculate this, this was 58 degrees. And so this leg over here should be longer than this leg over here. And 19,000 is longer than 12,000, so I think it checks out. Now, if you don't like that little trading places move that I did earlier, you could go old school and you could put a 1 under this and now just cross multiply and do 12,000 equals x times tangent of 32. And then solve it, since this is multiply, solve it by dividing both sides by tan of 32. And you'll notice that you get the exact same piece either way. So when x is on bottom, you can always trade places. Alright. Moving down to the last problem. And oh, this problem's got a star beside it, so it must be a little bit tough. So let's see what we're dealing with here. A bird is flying at a height of 40 feet, spots an 8-foot ledge on which to perch. So 40 feet, got an 8-foot ledge. So let me put the ground. I'm going to put a ledge over here. That's 8 feet high. Bird is up here flying. Caw-caw. I'm a little bird. If the top of the ledge is at a 22 angle of depression from the bird, so angle of depression from the bird, we got to do our horizontal line, and we know that depression means down, so bird's coming down to land on the ledge. So this is my angle of depression, which is 22 degrees. So 22 degrees. Typically, your angle of depression isn't in the triangle that you actually need. If the top of the ledge is, how far must the bird fly before it can land? So how far can the bird fly? We're actually wanting to find the length of this blue line. All right. So we're going to call this blue line here X. That's how far it is from the bird to the ledge. And the bird is flying at a 40 feet height. So the bird over here is 40 feet from the ground. Well, really, my shape right now is not even a triangle. My shape is a quadrilateral. It's got 4 sides to it. It's got 1, 2, 3, and up here is 4. So what I need to do is I need to draw a line over right here and come across to make myself a triangle. And now I'm going to do a couple important things, and this is big. If this total height here was 40, and I know this piece down here is 8, I can use subtraction to find out that this piece is 32 feet. Alright, so I'm going to put that in red. This piece right here is 32 feet. And then the next thing I'm going to do is I'm going to transfer my angle of depression down here because they're alternate interior angles. And now I believe I can solve this problem. And I'm going to just kind of come over to the side, and sometimes I do this when I get a whole bunch of stuff going on. I simply come over here and now draw what matters. What matters is I have a 22 there, I have a 32 here, and I'm trying to find X. This should make my problem quite a bit easier. So point of reference, or your guy, goes here. This is going to be the opposite. This is going to be the hypotenuse. Opposite and hypotenuse, well, that is sine. The sine when standing at 22 degrees is the opposite over the hypotenuse. I'm going to use the trading places method that I used earlier. If X is on bottom, these two can just trade places. And X equals 32 divided by the sine of 22 degrees. Pop that into my calculator. 32 divided by the sine of 22 equals 85.42. And it said, didn't ask, so 85.42, and this problem is talking about feet. Alright, so there you go. There's 4 examples of elevation depression problems, and hopefully that's enough to get you rolling on the 8-6 practice. See ya.